everyone, welcome to this afternoon's GCSE Physics live group tutorial. The topic today is reflection and refraction. It's great to see lots of you joining us this afternoon. Welcome back if you've been to one of these live group tutorials before, and welcome if this is your first time. My name's Tilly and I work at My Tutor. I'll just be here to answer any questions throughout the tutorial that you have about the My Tutor online school. These tutorials are designed to keep you learning during this time and to give you some really good deep dive into the content of your GCSE studies. At the moment we're doing science, maths and English, and we'll soon be branching out into other subjects, so watch this space. This session will be 1 hour long, so we'll finish at 3 p.m. And if you have any questions for myself or the tutor throughout, just pop those into the chat box at the bottom or the Q&A, and we'll make sure to answer as many of those as we can. So your tutor this afternoon is Preshayla, who studies physics at Loughborough University, and this is her 4th year as a tutor. So it should be a great session today. And hopefully you guys are all able to access the chat today to ask any questions. Brilliant. So lots to cover today in terms of content. So what we'll cover is understanding the key features of reflection, understanding the key features of refraction, understanding absorption, being able to describe the required practical, and then some example questions at the end, followed by any questions you guys might have about anything that's been covered throughout. So without further ado, if you're all ready, Preshayla, let's kick off the session.
Cool. Okay, so yeah, as Tilly mentioned, we're going to be doing reflection and refraction today, and that's not all. We'll also talk a little bit about transmission and absorption. There's not any equations per se in this topic, so not much to kind of memorize in the way of equations, but more kind of wordy, qualitative stuff. So yeah, we'll get started with reflection. So reflection is quite simple, really. It's a wave that hits a reflective surface, so a mirror or some kind of other type of reflective surface, and it gets reflected back. Okay, so it hits a boundary to be reflected between two different materials. Usually it's going to be air and a mirror, or air and maybe another reflective surface, air and a wall, something like that. Okay, so it's a boundary between two different materials. So the wave hits the boundary and it gets reflected back. Okay, and light and sound waves can both be reflected at the boundary. So when you hear an echo, that's a sound wave being reflected, and the same when you look in a mirror, that's the light wave being reflected. So the light hits the mirror and comes back into your eyes so that you can see your reflection. So that's two examples of how reflection works in light waves and sound waves. And then we have a law. So not really kind of an equation, but a law, which says that the angle of incidence, don't worry if you don't know what the angle of incidence is yet, equals the angle of reflection. So what that means is the angle that the light ray enters is the same as the angle that it reflects with. And you'll see a diagram in the next slide to kind of help you visualize that, but that's the law of reflection. So wherever we have a mirror or a reflective surface, the angle that it comes in at is the same angle it's going to leave at. So if a light ray hits the surface at 56 degrees, it will also be reflected at 56 degrees. Now, the important thing to remember when we're talking about ray diagrams, which you'll see quite a lot later on, is that the angle of incidence, the angle of reflection, the angle of refraction, we have 3 types, is always measured between the light ray, which is like a straight line with an arrow on, and the normal. Okay, so the angle is always measured between the light ray and the normal. Okay, so that's a really important fact that we need to remember. So it's not just any old angle, it's that specific angle so that they match, so that the angle of incidence and the angle of reflection matches. Okay, so I'm going to take you through step by step how to draw a ray diagram for a reflective surface. Okay, so this is a really, really important part of the topic. I can't stress enough how important ray diagrams are, not only in this topic, so not only in reflection and refraction, but also later on in the week we're going to be doing lenses, and ray diagrams become even more important then. So it's really important that we know how to draw them perfectly. So this is the ray diagram for a reflective surface, i.e. most likely going to be a mirror. Okay, so that's the ray diagram for a reflective surface that we're now going to draw. So we start off with our reflective surface. So that's this pink rectangle here. That's our medium. So medium is just kind of a fancy word for the material that the light is going into or being reflected off. So this is our medium, which is the mirror. Air is also a medium. So air is all this space around here. So basically what we have is a light traveling through air. So light beam traveling through air, hitting the medium, which is in this case a mirror, and reflecting back off. Okay, so that's what we kind of need to depict in our diagram, is a ray coming in and being reflected off at the same angle. So it's going to look a little something like this. We have a light ray coming in and the light ray coming out. Okay, and you can see that they're at the same angle to the normal. That's the same angle there as it is the same angle there. Okay, so that's really important when you're drawing the ray diagram for reflection. Only for reflection, the angles need to be the same. Refraction is different, but for reflection, it's the same angle. Notice that it never actually enters the medium. It never actually enters the mirror. It just gets reflected off just there. Okay. So here we've got our mirror. Now, does anybody know what this purple line through the middle is? If you know what the purple line through the middle is, put it on the chat. It's not just a random line, it's got a name. Great, loads of you seem to know what it is. Good, it's the normal. So the normal is the line which is at 90 degrees to the medium. Okay, the medium that we're dealing with. In this case, it's a mirror. Later on, we might be dealing with glass or water. In this case, it's a mirror. So we draw our normal to the mirror. And the normal has lots of purposes, but I think primarily its main purpose is to really help us to line everything up and to get our light rays in the correct place. So we know that we're going to have one light ray going towards the normal and one light ray going away from the normal. And as well as that, we need to put the normal in because that's how we're going to measure the angle. Yeah, remember the angle, if we go back to the other slide, the angle is measured between the light ray and the normal. Okay, so the angle is measured between the light ray and the normal. This is the light ray, this is the normal, so this is the angle. Same again here, this is the light ray, this is the normal, so this is the angle. So the angle of incidence is here, the angle of reflection is here. Okay, so it's always the angle between the light ray and the normal. Not this angle here, that's between the light ray and the medium. We want the angle between the light ray and the normal. So angle of incidence on the left and angle of reflection on the right. Okay, so that is how to construct a basic ray diagram for a reflection off of a mirror. Might not be called a mirror in the exam, it might be just called a reflective surface, and in which case they are the same thing and it would be exactly the same ray diagram that you'd be expected to draw. So Key features of this then is we need to have a normal. So first step is put your normal in. Second step is draw your light rays. So one going in, one coming back out. So that's the incident ray on the left and the reflected ray on the right. So incident ray and reflected ray, draw them. Then put your angles in. And remember that angle is the angle between the light ray and the normal, where the angle of incidence is the one to the incident ray. And the angle of reflection is the angle between the reflective ray and the normal. Okay. So some waves won't be completely reflected, and actually in practice completely reflected waves aren't that common. Sometimes our rays are going to be absorbed or just go straight through the medium. Okay, so things that kind of affect whether a wave will be transmitted or absorbed is the type of wave that we're dealing with, so the type of wave that we're dealing with, the wavelength, the difference between the two media, so if it's a large difference or a small difference, so whether it's water and glass or water and air, and other properties of the wave determine what happens to the wave's energy. Is it going to go straight through the medium? Is it going to be completely absorbed by the medium? Is it going to be reflected? Is it going to be refracted? So lots of different things that can happen to our wave. And it's determined by the type of wave that it is, the wavelength of the wave, and the difference between the two media. Okay, so common examples of absorption are waves hitting the beach and giving their energy to the sand. So as soon as you see a wave come in, it crashes into the sand and it gives all the energy to the sand. If the wave's not reflected and it's not transmitted, so the wave doesn't come through the sand, it doesn't keep going through the sand, and it doesn't get reflected, so we know that it's absorbed into the sand. The energy is absorbed into the sand. And the same thing with sunlight landing on a face. So when you feel the sun hit your face, it's going to be absorbed by your skin and warm it up. So that's another example of absorption. It doesn't get transmitted, otherwise that would be very dangerous. And it obviously doesn't get reflected because our faces are not reflective surfaces. Okay, and then another one is sound waves hitting a thick material like curtains. So curtains are just one example of a material that might absorb the sound waves. So they get completely absorbed and the sound gets muffled. Okay, and then some examples of the transmission of energy. Well, the transmission of energy can happen in sea waves passing a shallow area. So they could just continue to wave in a shallow area. Light passing through a glass window. So the whole purpose of a window is to transmit light, right? The whole purpose of a window is to allow light to come through. So that's an example of transmission. And obviously we want as much light from the window to come through. And then ultrasound waves scanning a baby. So we obviously want ultrasound waves to go in to the womb and come back out of the womb as well, so that we can detect the echo. So it needs to be, ultrasound waves need to be able to be transmitted through the body. So that's another example of transmission. I would recommend remembering these examples because you may be asked to give examples of where absorption and transmission occur in day-to-day life. So either I would say just remember a few examples, have them in the back of your head, ready to pull out for when you do need to answer an exam question about absorption or transmission. Okay, and I've put at the bottom here, this is a higher tier kind of question and statement. So sometimes in the higher exams, so if you are on higher, which I think most of you will be, we need to know that shorter wavelengths transmit better through glass, and vice versa, longer wavelengths transmit worse through glass. Okay, so shorter wavelengths are more likely to go through glass. So that's another kind of important statement, but that is only for higher. So if you're not doing higher, don't worry about that. Okay, so sometimes light is not reflected, it's refracted. So there's a big difference between reflection and refraction. Refraction is a change in direction of a wave when it hits a boundary between two transparent materials. So there's quite a lot of key terms in this statement, and it is a very good formal definition for you to put in your exam. So refraction is a change in direction of a wave when it hits a boundary between two transparent materials. So glass, water and air are the ones that you'll be dealing with in your GCSE. So water, glass and air are going to be the things that refract light, that bend light. Okay, so again, we're going to go through step by step a refraction ray diagram. So could we put the, okay. So we're going to have an angle of incidence coming in, like so. So that's the incidence coming through there. Okay, so this is air up here. And this is glass down here, or water, whatever you want it to be. Okay, so we have our light ray coming in. Again, it's an incident ray. Then we have the refracted ray. So the light bends and goes off at a different angle. Okay, so it's not like reflection where the angles are the same. It's refraction where the angle is now shallower. But we still measure the angles from the light ray to the normal. That never changes. So the angle from the light ray to the normal is there, and that's the angle of incidence. This time, the angle from the light ray to the normal is here, and that's the angle of refraction. So you can see it more clearly here. The angle of incidence is this one here, and the angle of refraction is this one here. So remember, this is always happens on the boundary between two mediums. So this is the boundary here between two transparent mediums. So in this case, we have air and glass. This could be replaced for water. Notice that the bending of the light bends towards the normal. And if you don't understand what bend towards the normal is, this never got explained to me properly in school, so completely get it if you don't understand it. But basically what we mean by bends towards the normal is if we were to carry on this angle of incidence, you can see that this ray is closer to the normal, right? It's not bending on the other side of this line. It's not going that way. It's bending towards the normal. Okay, so it's closer to the normal than over here. So if you were to carry it on, the refracted ray is closer to the normal. Now that's not always the case. Sometimes it does go the other way. And we have an acronym, or I don't know, it's called a mnemonic, that helps us remember it. Okay, so this is again higher. So if you're in higher, you need to know how to explain refraction, not just what refraction is and how to draw it, but also how to explain it. So the density of a material affects the speed of a wave traveling through it. So if we have a denser material, we have a slower wave. And that makes sense, right? If the wave is trying to get through particles which are more closely squished together. So I told you that we have the three kind of transparent materials of air, water, and glass. Well, that's liquid, gas, and solid, right? We have gas of air, liquid of water, and solid of glass, and they get denser as you go along, which means that the wave travels slower. Okay, so we have air, water, and glass, and the wave travels slower as we go from air to water to glass. So the density of a material, or how closely packed the particles in the material are, affect the speed of the wave. Okay, so because glass is denser than air, the light wave slows down. Okay, so because glass is denser than air, the light wave slows down. So in our example, let's go back to it. Glass is denser than air, which means that the light wave has slowed down in the glass. This causes it to refract. Okay, so that causes it to refract. Now, I said previously that the refracted ray can either go towards the normal or away from the normal. So in the diagram, we had it going towards the normal. Sometimes, though, it will go the other way. How do we know which way it goes? How do we know whether it's going to go away from the normal or towards the normal? If you know the answer, put it in the chat if you know. So how do we know whether it goes towards the normal or away from the normal? Okay, loads of you are putting really great answers in, which is really good. That was quite a complicated concept and a complicated question to go with it, so that's really good. The way I like to remember it is with the mnemonic FAST, so F-A-S-T, where F stands for faster, A stands for away, S stands for slower, and T stands for towards. Okay, and the first two match and the second two match. So faster away, if the light wave travels faster, if the light wave gets faster, which means the density gets less, then it bends away from the normal. If the light wave travels slower, then it bends towards the normal. So along with faster and away, we have the idea of density. So faster away is a lower density, slower towards is a higher density. So I'll just explain that again, because it is, again, quite a confusing concept at first. So faster, if the wave is traveling faster, it's going through a lower density material. So something like air. The wave can travel much faster in air than it can in glass because the density is much lower. So the light wave bends away from the normal. The second part of the mnemonic is if the wave travels slower, then it's going through a higher density material. So something like it going from air into glass, because glass is a higher density material than air. So the light wave slows down. It can't get through glass as easily as it can through air. So it must go slower. Because we have a slower wave, the light ray bends towards the normal. And that's exactly what we had in our diagram. The wave goes slower because it's entering a more dense material and therefore bends towards the normal. It's bending this way, not this way. Okay. Okay, so now we are kind of going to show refraction with these things called wave fronts. So wave fronts are basically just a way of you depicting a wave without drawing out the whole wave. Okay, so what I mean by that is we've got a wave traveling through space, but imagine you're stood here and the wave is traveling towards you, right? This is your eye here and the wave is traveling towards you. You will only be able to see a straight line. Hopefully that makes sense. You need to put yourself in the kind of eyes of visualizing the wave from here. So a head-on view of the wave, which is traveling towards you like this. So you're only going to be able to see a straight line. Okay, now that is how we explain a wave front. The wave front is basically just a way of us showing the wave without drawing all the squiggly lines and making it look really messy. So wave fronts are a nice way to neaten it up and show exactly what happens to the wave without having to draw all the squiggles. Okay, so we can show refraction with wave fronts. We already showed it with light rays. Now we're going to show it with wave fronts. So this is the second way of showing refraction. Okay, so this is what it looks like. We have wave fronts traveling through air at a constant distance apart, right? It's a constant wavelength between the wave fronts. So that distance, okay, that arrow is really big. Hold on. Okay, that distance between two wave fronts is the wavelength. Okay, and you can see that it's at a constant wavelength. Here, 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 they all match until it hits the boundary. Okay, now when the wavefront starts to move into the glass, you can see that it bends, right? It starts to bend. The parts of the wave that start to hit the boundary slow down because, again, we're going into a denser material, so the wave slows down. They start to get closer together and their wavelength gets smaller. So remember, the distance between the wavefronts is the wavelength, and we can clearly see that the wavelength gets smaller. Okay, so if the wavelength gets smaller, the speed also gets smaller and vice versa. So the wave is slowing down, and if you take our equation v equals f lambda, okay, so we have the wave slowing down because it's in a denser material. If the wave slows down, what needs to happen to the wavelength? For the same frequency, the wavelength must get smaller. Okay, so if the wave speed gets smaller, remember v is just wave speed. If the wave speed gets smaller or slower, the wavelength must also get smaller. Okay, so that's exactly what happens when we go from air to glass. So this is showing refraction. It's still showing the exact same thing as we had in this diagram, but in a very different way by using wave fronts. Okay, try to, after the webinar, recreate this diagram for yourself. So draw some parallel lines, and then as soon as those lines start to hit the boundary, start drawing them refracted. And you won't even need to draw them closer together. Just simply by you changing the angle of the line, you'll see them start to get closer together. So try and draw this diagram for yourself, because I think it really helps in understanding the fact that these get closer together. And that shows that the wavelength gets smaller and shorter, and we know that the wave speed also gets smaller. Okay, so some complicated ideas there. So I'm just going to take a break for questions on any of the content that we've covered. If you want me to go back to the slide, please do so.
Cool, there have been a few questions throughout, and apologies if these have been answered, but just want to make sure they get covered. Do waves always slow down when going from air to another medium?
Okay, so it depends on what the other medium is. So if it's a denser medium, like glass or water, basically anything, because anything's denser than air, right? A liquid is denser than a gas, and a solid is denser than a gas. So any liquid, any solid is denser than air. If it's denser, it travels slower. So waves always slow down when they're going from air into a denser medium.
Great, and why do short wavelengths travel better through glass?
Okay, so that's kind of outside of your specification, as it were, and above the GCSE level, but we are going to cover it later on in the week, so stay tuned for that.
Great. Someone asked earlier on, this is quite early on, how would you describe the normal in an exam?
Okay, so the normal is simply a perpendicular line to the medium in which the light ray enters, or gets reflected off of, or is refracted into, or is transmitted through, or absorbed in. So it's the kind of medium that we're dealing with. It's just a perpendicular line that we draw on the medium.
Great, and we've had, what does V equals Fy mean?
Okay, so that's V equals F lambda. If you were here yesterday, we did go through it, but if you weren't, not to worry. V is velocity. So V stands for velocity, but formally we call it wave speed. So it's the velocity of the wave, which is wave speed. And then F is frequency. So F is frequency, and that's not a Y, that's a Greek letter called lambda. Okay, so that's called lambda, but it actually physically means wavelength. So lambda is wavelength. So we have wave speed equals frequency times wavelength, where wave speed is measured in meters per second, frequency is measured in hertz, and wavelength is measured in meters.
Thank you. And is there an equation for reflection and refraction?
So reflection, the equation that you kind of need to follow is the law of reflection, which is angle of incidence equals angle of reflection. So that's the law, not really equation. I wouldn't really call it an equation. It's just a law that says that the light ray that comes in leaves at the same angle that it came in at. Okay, so that's the kind of equation for reflection. There is an equation for refraction, but luckily you don't need to know it. So that's all good.
Cool, and just a couple more before we move on. Can air and glass both be replaced with water?
I'm not too sure what they mean by that question. Could you clarify in the chat what you mean by air and glass being replaced by water? Oh, for the wavefront diagram. Yeah? Okay. Okay, so for the wavefront diagram, air can't be, okay, I get what you mean. So air can't be replaced by water. Water can go in here instead of glass. So we can have air refracting into glass and air refracting into water. So the light can come from air into glass or air into water. And actually there's a nice diagram that shows this, if I can find it. Yeah, here. So what we have here is air to glass to water. All right, we have air here to glass here to water inside the cup. So we can see that we've got a refraction from air to glass and then a refraction from glass to water. So in our diagram, yes, the glass can be replaced with water, but the light ray needs to be able to refract between two mediums. Okay, so it needs to be able to refract between two mediums. Whatever mediums that you choose to have, make sure that your wavelengths match up. So let's say you have water on top and then glass. That's going from a less dense to a more dense. So the wave slows down and the wavelengths get shorter. So yes, you can have any two materials that you want here, but make sure that you know which one is more dense, which one is less dense, so that you know how far apart the wavelengths need to be. Hopefully that makes sense.
Cool. And just to follow up to that, a couple of people asking what would the wave diagram between water and glass look like, and would this look different?
So no, water and glass would look the same because it's going from less dense to more dense. It doesn't actually matter too much what the materials are for wavefront diagrams. So if it was water to glass, it would look pretty much the same because you're going from a less dense material to a more dense material. However, if you had glass to air, that's going to look different. And it's going to be shorter wavelengths here, going to bigger wavelengths underneath.
Brilliant. And just one more for now, and then we'll come back and answer remaining questions at the end of the session. The question was, where has it gone? Ah, yes, for the wavefront diagram, could you clarify where the normal is?
Okay, so for wavefront diagrams, we don't actually tend to draw a normal. It's not kind of required in a wavefront diagram. So we don't really, I mean, if you really wanted to draw it, you could draw it, I guess, going down like this. So it's still at 90 degrees to the medium, right? It's always at 90 degrees to the medium that we're dealing with. So here we're dealing with glass. I'll draw it a bit better for you. So it's going to be a 90-degree line going down there. Okay, so that's where the normal would be. But you don't need to draw it when you're drawing wavefront diagrams. It's not necessary. But again, always at 90 degrees to the medium if you're in doubt.
Cool, brilliant. Should we carry on with content and then go back to questions at the end?
Let's carry on with some
Thanks,
more
Preshayla.
content. Okay, so the required practical, actually not as bad as it looks. You might have done it in school, you might not have, but this is the required practical that is associated with refraction and reflection. Okay, so we have a ray box, which is basically a source of light. It's like a little bulb inside a box. The box is just there to kind of contain the light, and then we put a narrow kind of slit. So it's a metal square with a slit cut out of it, a narrow slit cut out of it, which goes in front of the ray box. And all that does is let you have a thin beam of light so that we can clearly see the beams of light coming through. Yeah, so if we weren't to have a slit there, it would just be lots of light being spread out everywhere, and it wouldn't actually help us to see the light rays. So by putting the slit there, we can have nice, neat, narrow light rays. Okay, so first step is to set up the ray box, set up the slit, and have these narrow light rays being produced. We'll have a ruler with us, and basically what we want to have is underneath all of this is a big A3 piece of paper, right? So you're doing all of this on an A3 bit of paper, and that will become clearer why we do it on A3 paper later. So imagine a big piece of paper underneath all of this. On that piece of paper, we're going to draw a normal. Okay, so our normal, we're going to label, and we'll draw it perpendicular to the edge of the paper, if that makes sense. So a normal to the edge of the paper. Then we're going to place our acrylic block on top of that normal, so that the normal lies about halfway along the acrylic block. Okay, so our acrylic block or glass block is, it goes through the middle, so the normal needs to line up with the center roughly, and that is where our normal will sit. Then we want to draw around the block. After we've drawn around the block, we obviously don't want to move anything, because then we have to keep drawing around the block and it just gets annoying. So when we are going to finalize drawing around the block, we need to make sure that everything matches up. Then we can start to use the ray box. So we'll turn on our ray box and we're going to shine a beam of light into the block. Now some of it will be refracted, which you can see is this line here. That's the refracted ray. Some of it will be reflected. That's the reflected ray. So we can have reflection and refraction. So there's 3 rays going on here. Incident ray, which is this one here. That's our incident ray. Reflected ray, which is this one here. Reflected. And refracted ray, which is this one here, which bends. Okay. So we've got 3 different rays which are marked with an X here. Now, to mark where those kind of rays are, you have to draw a mark on the piece of paper. That's why we have the piece of paper underneath. We're going to mark out with a little dash or whatever where the light ray is. So you'll be able to see the light ray on the paper, and you want to mark where it is in the incident, mark where it is reflected, and mark where it is refracted. So we're going to have reflection and refraction at the same time. Okay, we're going to have 3 different angles that we need to measure. Once we've drawn the little dash, we can move our acrylic block away. Then we're going to draw a line from each of the little dashes that we made and make them all meet up. So you want to mark the path of the incident ray with a cross or a dash, mark the path of the reflected ray with a cross or a dash, and the ray that leaves the block, so this one here. Okay. Remove the block and join the paths up with long lines. And then you're going to measure the angle to the normal. So you're going to have to record 3 different angles in a table. The first being this angle here between the angle of incidence and the normal. The second being this angle here, which is the angle between the reflected ray and the normal. And finally, this angle here, which is the angle between the normal and the refracted ray. So we have 3 different angles that need to be measured. They can be measured with a protractor as long as they are measured towards from the normal. So here we've got the incident angle, here we've got the reflected angle, and here we've got the refracted angle. Okay, so quite a kind of complex practical experiment that we have. I would recommend, if you don't quite understand it, watching the practical actually take place. So there's lots and lots of videos on YouTube for you to kind of go and have a look at and actually watch the practical take place, because it's all good and well me explaining the method to you, but until you kind of actually see it, I feel like you don't completely understand it. It is a very important practical to remember and to kind of understand. Now, the whole point of this practical is that we do it with different types of material. Okay, we're trying to see the relation between the incidence, reflected and refracted rays for different blocks. So we're going to start with an acrylic block, then we might replace it with a glass block, and maybe some other types of transparent solid materials. So the glass block really just is there as a pathway to see the light ray being either reflected or refracted. So it's there as the material that we're testing on. It's the medium that we're testing on. Okay, so hopefully that makes sense. Okay, so we're going to go through a few questions now so that we can consolidate your guys' learning and understanding, and really iron out any misconceptions, of which there can be a lot for this topic, because it is quite, as I said, complicated, and there's a lot of new complicated ideas that you've not met before. So if you could, please just put your answers in the chat, or have a think about it to yourself if you don't want to. And we're just going to go through these 8 quick-fire questions. So what is the name of a line drawn at 90 degrees to the surface of a material? That is the normal, absolutely. Which term is used to refer to an incoming ray incident? Cool. Well done to those of you that got that right, and I think that was every single person, which is really good. And then the next ones, what is the law of reflection? So that equation for reflection, but not really, more of a law. And which is the most dense, air, water, or glass? Great, again, loads of you are getting it absolutely correct. I don't think anyone's got it wrong so far. This is really good. So the law of reflection is the angle of incidence equals the angle of reflection. So the angle that it comes in at is the same angle that it leaves at. Which is densest, air, water, or glass? Glass. If you're struggling to kind of think about it in terms of materials, just think about it as gas, liquid, and solid. Just go back to kind of year 7 when you first started out learning about materials. You learned that gas is less dense than liquid, liquid is less dense than solid. Okay, so next one. What happens to a light ray when it travels from water into air? So remember your mnemonic, fast. So it's going from water to air. It's going from a more dense medium to a less dense medium. So if it goes from more dense to less dense, the wave is going to be able to travel faster, not got as much kind of resistance. And if it can travel faster, it bends away from the normal. So faster away. And which word is used to describe a light ray being passed through a material? That's transmission. So when it is allowed to go through the material. Okay, a light ray meets a mirror at 60 degrees. What is the angle of reflection? Great, it's 60. That is the law of reflection. Angle of incidence equals angle of reflection. And a light ray passes from air into water at an angle of 30 degrees. So it's going from air into water. So it's going from a less dense to a more dense medium, which means it's going to travel slower, which means it's going to go towards the normal. So the angle is going to be much smaller. Yeah, so if we think about our refraction diagram here, the angle of refraction is smaller than the angle of incidence because it goes towards the normal. If it was bigger, it would be going away from the normal. So the answer is 22 degrees because it goes towards the material, because it goes into a more dense medium, which means the wave travels slower, and it's at ST of fast. Okay, so here we are given some information from an investigation that was conducted about the refraction of light when it goes from air to glass. So that diagram that we had before is exactly the investigation that the student did, and they've given you a table of angle of incidence and angle of refraction. Why is the light refracted as it crosses from air to glass? Great. For those of you that said that it travels slower, that is absolutely correct. And you've even gone one step further to say that the density is higher. So just to get this mark, all you need to say is that the wave travels slower, but you guys have gone kind of one step further and said that because it's more dense, that means it travels slower, which is really great. So yes, the reason that refraction happens is because it's traveling into a more dense or less dense medium and therefore going slower or faster. Okay, so here we have a diagram of a glass block, a ray box, an incident ray. So it's going from air into glass. Which way is the light ray going to go? What is the light ray going to look like? If it's going from a less dense to a more dense medium, okay, so loads of you getting the right answers now, which is really great. Yes, we're going from a less dense to a more dense medium. If we're going through a more dense medium, the wave slows down. And from fast, we know that if it slows down, it bends towards the material. So it goes like that. Sorry, not towards the material, towards the normal. So it goes like that. What we mean by bend towards normal is that if you were to carry on this incident ray, it wouldn't go this side of the ray, it will go the normal side of the ray. So it would go towards the normal, not towards the other side, wherever it is. Okay, so that's where the refractive ray would go. Okay, so going to stop there, take some more questions from you guys, so put them in the chat or put them on the Q&A. Again.
Well, we had a few on the practical before.
Mm-hmm.
So one was just, what would we call the practical when searching up the video?
Okay, so you want to, so you wanted to say investigating incident rays and refracted rays in different transparent mediums. But that's the formal name of the experiment. But if you just type in GCSE AQA required practical light waves, is going to come up. There's only one to do with light waves, to do with reflection and refraction, so it will come up. You'll find it straight away.
Cool. And what is the role of the glass box in the practical?
So the glass block is really just there as a medium to kind of experiment with, to show the light rays moving around. So if we didn't have the glass block there, we just have a light ray that just goes along the paper. It'd be a really boring experiment and we wouldn't have anything to experiment with. So the glass block is there as a medium for which to allow light to go through. So the glass block reflects a bit of the light, it refracts a bit of the light, and we can do kind of measurements with it. So it's really the fundamental part of the experiment. The glass block is then switched out with an acrylic block, and we do the experiment again with different materials. So the whole experiment is really about using different materials and seeing how the light behaves in different materials.
Cool. And a couple of questions from someone. How would you improve the glass block practical, and what are the control variables for the required experiment?
Okay, so for the controlled variables, that's going to be the block. So for one whole kind of experiment, you're going to keep the block the same. You're going to keep it in the same place. The ray box is always going to stay in the same place. The normal's going to stay in the same place. Piece of paper is going to stay in the same place. All the positioning is kind of going to stay the same. And then when we start on the kind of second part of the experiment, that's when you switch out the glass block with the acrylic block. So yes, it is the control whilst you're taking data, but then it's changed for the acrylic block. So in that way, it is kind of the thing that we are changing. But whilst you're taking data, you don't change the block. You have one block, you take the data, you change the block, you take the data again. Okay, so control variables would be where the glass block is, where the normal is, where the ray box is, the piece of paper, the person who's doing it, those kind of things really. And then how would you make it better? So just to be as kind of accurate as you can when drawing the crosses and joining them up together, making sure that that nothing is nudged, and possibly using different kind of medium, so not just a glass block and a acrylic block. You could use water, you could use kind of like a tray of water and experiment with that as well.
Cool. And can reflection and refraction happen at the same time during the practical?
Yeah, so that is the kind of whole idea of the practical, that it does reflect a bit of light and it refracts a bit of light. So as I said, in practice, it's actually not very common to have all of the light being reflected unless it's a mirror. In practice, actually, some of it's going to be refracted through. Some of it might be reflected back off, just because of the nature of the material. It's not going to allow all of it to be refracted. It's going to actually push some of it back out and reflect it.
Nice. And would you need a result table for the required practical?
Yeah, you always need a result table with any experiment that you do. So the result table would just be a 3-column kind of results table like this. And you'd have the angle of incidence, the angle of refraction, and the angle of reflection. So 3 kind of column table, and just put your angle in each, and that's all you need to do.
Cool. A couple of questions just to wrap up. So can sound refract?
Yeah, all types of waves can be refracted. So yeah, sound waves, light waves, anything.
Brilliant. Just a couple of people asking, could you go back to question 7?
Yeah, question 7. Okay, so question 7 is the law of reflection. So we've got a mirror and we've got a light ray coming into it. Because it's a mirror, the light ray gets reflected back off of it. We draw our normal in and we measure the angle between the light ray and the normal, and the light ray and the normal. So we've got one light ray going in, one light ray going out. Now this angle of incidence is 60 degrees. The light ray meets the mirror at an angle of 60 degrees. So that is 60 degrees. And because of the law of reflection, the law of reflection says that the angle of incidence equals the angle of reflection. So that must mean that this is 60 degrees as well.
Great. Just finally, could you explain fast again?
Fast again. So fast. Okay. So faster away, slower towards. So if our wave goes from a higher density material to a lower density material, it travels faster. Okay, it can travel faster because it's a lower density material. The particles are not as packed together. So faster away. and then slower towards. So slower is if it goes from a lower density material to a higher density material. The wave travels slower and it bends towards the normal.
Brilliant. Okay, I think we're going to have to wrap up there, but thank you so much for all the great questions throughout this session. Just a reminder for people sort of asking to go back to previous slides and stuff, and this has been recorded. It will be uploaded to the My Tutor YouTube channel by the end of today, so by 6 p.m. So you can just watch back, copy anything down, make notes, etc. And thank you so much for joining us today. If you want to join us for some other tutorials, whether it's GCSE physics or other subjects, then please do. For the My Tutor online school, we've got a really busy timetable tomorrow. We've got chemistry, English, maths, physics and biology. So it should be a really great day. So you can find those links to the tutorials on the site and also via your emails. So thanks so much everyone for joining, and thank you very much, Preshayla, for a fantastic session.
Thank you, everyone.
Thanks. See you guys soon. Bye.
Bye.